H of P looks like that, so 1 minus H of P looks like this. So this is C of a channel with cross error probability P. Okay, the first thing you ask yourself is, why isn't C of P equal to 1 minus P? In other words, I only have P errors, throw the errors out, and now I have 1 minus P places where there wasn't an error. Well, that's because I don't know where the errors are. So it's harder to distinguish two sequences where you know where the errors are and where you don't. So that dispenses with a cheap counter-argument that you can do better. Next thing we notice is this is 1 and this is 1. So if the channel makes no errors, that is P is 0, the capacity is 1 bit per use. Now here's an interesting thing. At a half, the capacity of the channel is 0. Why is that? Well, you put in your X sequence, and basically what comes out the other end is a coin flipping sequence that's independent of X. That's what P equals a half will do to the input of a 0 and to an input of a 1. It'll give you a probability distribution on Y, half a half. So you don't get anything through such a channel. It's 0. The next interesting thing to note is, say, if P is 1/3, it seems to have the same capacity as if P is 2/3. Now you see why that's true. Why is a channel that makes 95% errors as good as a channel that makes 5% errors? Well, this is like the weatherman that's always wrong. You just flip whatever he says. So you can, if it makes 95% errors, you just flip what Y is, 1 and 0, and now it's making 5% errors. Okay. All right, great. So that's why it's symmetric. And then the final thing I'd like to note is if P equals 0.11, then we get a half. This is just good to keep in mind. If you make 11% errors, you can get a half bit per use of the channel through. All right, number 2. Binary erasure channel. BEC. Here's one. I'm going to send a 1 or a 0. When I send a 1, it's going to get through with probability 1 minus alpha. But with probability alpha, I get an erasure. Alpha, 1 minus alpha, 0. So what's the capacity of this channel? By the way, here's a channel where you know where the errors are. But the error doesn't tell you what was sent. It just says there's an erasure. equivalent to the following problem. Suppose I have a treasure map that tells me where buried treasure is. And unfortunately, it gets waterlogged and torn up, and I'm left with a map with holes in it everywhere. I'm left with half a map. That is, alpha is a half. How many distinguishable treasure maps are there when you can only see half a map? And the answer is half a bit per use, or if you will, the map has n over 2 pixels left. It did have n, and it has n over 2. The number of bits you can get through that wholly torn up map is n over 2. You say, wait a minute. I didn't tell you where I tore the holes in the map. Which proportion, alpha equals half, of the map I threw away. And you're saying that you can then get as much information through as if you'd known ahead of time what parts I was going to throw away, and I just filled in those n over 2 bits to convey to you maximal information. And I say, yes, that's the case. The reason is that if you look at all 2 to the n maps before they're torn up, and you choose only 2 to the n over 2, that's n over 2 in the exponent, maps minus epsilon. These maps will be distinguishable when you look at only n over 2 bits. So I can tell which of these maps it is, as long as I'm not trying to distinguish 2 to the n maps, but only 2 to the n slash 2. Well, let's double check what the what the information capacity is here. It's I. All right. This is max I of xy. And I of xy for the binary erasure channel is h of y minus h of y given x. All right, if I know x, then y is just alpha bar alpha for 1 in the e. So I know immediately this is h of alpha. Now, what's h of y? Well, if I put an r here and a 1 minus r here for an arbitrary input distribution, then this is h of r alpha bar, r alpha plus r bar alpha, that's alpha, plus r bar alpha bar. Okay? Now, this can be decomposed into 2 experiments where you first do the alpha experiment, h of alpha, to distinguish this from these, plus with probability alpha bar, let's hope I get this right, Uh, all right, let me be willing to get it wrong, okay? Wouldn't be the first time. Alpha bar H of R. This is H of R bar. Good. Good. So this is just an identity. And now let's put these together. So this is, the H of alphas cancel. And then this is alpha bar H of R. Alpha I can't do anything about. It's the erasure probability. But R is the input distribution, and it shouldn't surprise you that we want a symmetric one. But look, H of R is less than H of half, which is 1 bit. So this is alpha bar. So therefore, C sub I equals 1 bit, alpha bar, bits per use, and it's achieved by P of X, probability X equals 1 equals a half. So, we've calculated now the capacity of the binary erasure channel and shown that it's just 1 minus the probability of an erasure. It's the probability of a non-erasure. It's the number of symbols to get through. And amazingly, for every symbol that gets through, we get a full bit of information. And that's due to the fact that these randomly chosen sequences of length n, since I only chose 2 to the n c of them, minus epsilon, are distinguishable when I only view n alpha, n alpha bar of the bits. And since they're distinguishable, I've indexed them. How many are there? To the n and c. So they're nc bits of index. So I get nc bits through in n transmissions. All right. Next time we will start to formally look at what is meant by operational channel capacity, and then go ahead and use joint typicality to prove that capacity can be achieved, and use Fano's inequality and a number of things to prove that you can't do any better, thus establishing Shannon's second theorem. Next time, of course, is next Tuesday. The midterm is 2 days from now. We'll have office hours 2 to 4. I'll have them 2 to 4 tomorrow. And the TAs are notifying people electronically when their office hours or availability is. Great. See you Tuesday.